Hi everyone, I'm Navid, and today I'll be talking about Sublime, our recent work on achieving sublinear error and space for unbounded and skewed streams. This is joint work with amazing colleagues at KTH University and the University of Copenhagen, and was fortunately declared as an honorable mention for SIGMOD 2026's Best Paper Award. In this work, we consider data streams, which prop up in all corners of computer science. These streams come from multiple sources, and they arrive with an extremely high velocity, which therefore makes the total amount of data too large to be stored in persistent storage. Even still, we'd like to reason about this data in real time. For example, in networking applications, we may want to analyze the stream of network packets that course through the links within our network. And in embedded systems, we may want to analyze sensor measurements collected over a long period of time. Depending on the application, we want to compute various statistics from the stream. Things like the min, the max, and the mean are easy to compute and maintain on the fly, but the problem becomes much more challenging when we want to track frequencies, cardinalities, quantiles, and so on. Computing these statistics requires more sophisticated techniques compared to maintaining a simple counter, as in the case of the min, max, and mean. In particular, computing these statistics exactly would require linear space or time in the stream's length, which, as we discussed at the beginning of the talk, is a prohibitive cost. People avoid this cost by employing data sketches, which approximate the desired statistic, use less space and time to do so, and provide a formal bound on the approximation error. Today, we'll be considering the specific problem of frequency estimation. Frequency refers to the number of occurrences of each item in the stream. This statistic has many applications in different domains. So for instance, in the context of a network, one may want to count the number of packets traveling to a given destination. Or in a social media platform, one may want to track the number of likes to a given post. These problems can be formulated as computing the frequency of the target of the packet or the like within a stream of packets and likes. A simple solution to computing frequency is to employ a dictionary that maps each key to its respective count within the stream. This method, however, has a space cost that scales linearly with the number of unique items we have in our stream. While the provided counts are exact, the incurred space cost is still expensive given the scale of data we have to deal with in the real world. This is where frequency estimation sketches come in. These sketches ingest a stream of keys, and given a query to a key, they estimate the frequency of the key within the ingested stream. Most importantly, they achieve this while avoiding storing full keys, and thus save a significant amount of space. Frequency estimation sketches have been studied from a theoretical perspective for many years, ever since the 1980s, and the many studied approaches are known to provide different types of error guarantees. So for instance, Mies always produces an underestimate of the frequency. Count sketch can both underestimate and overestimate, but it returns an unbiased estimate. And the count min sketch can only ever overestimate the frequency of the key. Today, we'll be focusing mainly on the count min sketch, though the approaches that we discuss are applicable to the other sketches as well. At its core, a count min sketch is a simple array of counters, each initialized to 0. When a new key is inserted into the stream, countMin maps that key to a counter using a hash function and increments that counter. So for example, the key A here is mapped to the second counter, and this counter will intuitively track A's frequency. Similarly, a different key B will be mapped to a counter as well, the third counter in this case, which it increments. And of course, if the same key is inserted twice, the same counter will be incremented twice. A count min sketch answers a query by simply returning the value of the counter that the query key hashes to. Here, for example, we get an exact estimate of B's frequency in this stream of ABA. However, since we may have hash collisions, the insertion of a new key C may actually inflate the value of B's counter, and, well, this causes the count min sketch to overestimate B's frequency later when it is queried. To reduce overestimation, count min sketch employs multiple counter arrays, each equipped with its own independent hash function. In this setup, when a new key A is inserted, it is mapped to a counter in each of those arrays using the corresponding hash function, and those counters are incremented. So after ingesting a number of insertions, one might end up with a state in the sketch like so. Now, when querying for a key B, count min sketch maps it to all of the counters across the arrays, and reports the minimum value as the estimate for B's frequency. In a sense, it returns the tightest overestimate that it finds across the arrays. When we use arrays with W counters to process a stream of n keys, we can actually show that the expected error we get within each array is equal to n over w. This is because the probability of a hash collision among two keys is 1 over w, so the total amount of overestimation after inserting n keys must be n times 1 over w, hence n over w. By applying Markov's inequality to this expectation, we can show that the probability that the error within this single array exceeds this threshold times Euler's number e is at most e to the negative 1. And, well, since we have, let's say, d-independent arrays, the probability that the minimum estimate exceeds this error bound actually becomes e to the negative d. So the probability goes down exponentially with the number of arrays that we use. Alright, so CountMin has many applications across many different domains, including but not limited to computing the heavy hitters of a stream, approximating the distribution of a dataset in machine learning, estimating the covariance of random variables, and detecting denial of service attacks in systems and networks. Because of this, the CountMin has garnered much attention from the research community in recent years, as you can see from the dramatic increase in the number of citations that it has received. But of course, CountMin has issues. Specifically, it has two core problems that we study in our work, skew and stream growth. The first problem of skew refers to how the sketch acts when processing a stream with skewed insertions. For example, in this stream, the key egg is inserted many more times compared to the other keys. If we use a classic CountMin to process this stream, all of the A's will map to the same counter, leading to a large value being stored within it. Meanwhile, all of the other infrequent keys will be dispersed across the other counters. This leads to some counters in the counter array being much larger than the rest due to representing frequent keys, while other counters are much smaller since they represent infrequent keys. In memory, if the counter array consists of fixed size counters, the binary representation of these counters will look like so. Here I'm showing you the lower order bits on the left and the higher order bits on the right. The problem with using fixed size counters on a skewed stream is that the many small counter values will consist of many unused leading zeros, which ultimately waste a significant amount of space. Ideally, we'd like each counter to be just long enough to store its value. There has been much prior work on addressing this issue, with approaches falling into the four categories of counter sharing, counter merging, hybrid methods, and compression-based methods. But all of these actually have a worse error bound and/or a worse speed compared to the original CountMin. So in a sense, they fall short of the ideal. Now, CountMin also has a second problem, and that occurs in the context of stream growth. Current CountMin deployments in practice use a fixed number of counters for the counter arrays within the sketch. Recall how doing so leads to an expected error of n over w when processing a stream of length n. That is to say, that error scales linearly with the length of the stream. So as the stream grows, the error also becomes worse and worse over time. Furthermore, we also cannot curb the error by constructing a larger sketch from scratch, since we don't have access to the original stream due to its large volume. Surprisingly, this problem hasn't been studied in the sketch world before, so we're very excited to be the first to consider it. To recap, we had two problems: skew wasted space, and stream growth worsened the estimation error. So the question becomes, how do we keep both the space and the error modest as the stream grows? We answer this question by presenting Sublime, a novel and general framework for achieving sublinear error in space for unbounded and skewed streams using frequency estimation sketches. Sublime addresses the discussed problems using two complementary techniques. For the problem of skew, it implements variable length counters to get rid of the unused leading zeros. Specifically, it takes each counter array it works with and splits it into chunks. It encodes the counters of each chunk within a single cache line, and within each chunk, it stores extendable counters. Specifically, we start by storing an array of short counters with a default length. Here, I'm showing an example of 4-bit counters as the default. We use this array of short counters to handle insertions as usual. But of course, as we increment the counters, we need some mechanism to handle overflows. We track which counters have overflowed by storing an overflows bitmap at the beginning of the cache line, which stores a 1 for each overflowing counter and a 0 for each of the other counters. Then, we store the overflowing bits of the overflowing counters by treating the remaining space towards the end of the cache line as an extension pool. Note that all of this is stored within the same cache line, so accessing these fields together can be done inexpensively. Now back to our example. We'll store the overflowing bits of the second counter here as an extension in the extension pool. In the extension pool, we form extensions from 2-bit fragments. We treat the fragment 1, 1 as a special delimiter that delimits the extensions. And we use the other 3 combinations of the fragments to represent the overflowing bits in base 3. So 0, 0 corresponds to the base 3 digit 0, 1, 0 to 1, and 0, 1 to 2. When we have the value x stored in an s-bit short counter, and an extension formed from fragments e1, e2, and so on, the counter's value can be derived as x plus 2 to the s times the decoded value of the overflowing bits in base 3, which is e1 times 3 to the 0 plus e2 times 3 to the 1, and so on. When we get another overflow after more insertions, we simply set the corresponding bit in the overflows bitmap to 1 and add the overflowing significant bits to the extension pool. While doing so, we ensure that the extensions follow the same ordering as their counters. This allows us to locate the extension of a counter by skipping the extensions of all overflowing counters to its left. Now, we can actually do this using simple looping, but that turns out to be slow as it involves many CPU instructions and branch mispredictions caused by looping. So we speed up this process using rank and select primitives, which are known to have very fast CPU implementations that leverage special instructions. Rank of I within a bitmap is defined as the number of ones before the ith bit of that bitmap, and select of j within a bitmap is defined as the offset of the jth one in that bitmap. So, if we want to find the extension of the ith counter, let's say, we first apply rank to the overflows bitmap to determine how many counters have overflowed before our target, which we'll denote by j. Then, we'll apply select of j to the extension pool to skip over the first j extensions and arrive at our target's extension. But of course, select doesn't just work out of the box like that, so we have to do some extra processing to make this procedure work. To illustrate the idea, let's work with an example. What we're going to do to enable applying select is to first make a duplicate of the extension pool. Then we'll shift the duplicate 1 bit to the right, and compute the bitwise AND of this shifted version with the original extension pool. The result is a new bitmap which has a 1 for every 1, 1 in the original extension pool. Now the ones in this bitmap that are at odd positions don't actually correspond to delimiters, as shown here. So we simply mask them out to compute a bitmap that has a 1 at the position of every delimiter. Applying select to this delimiters bitmap then allows us to find the extension of our target, and from that point, we can simply decode the value of that extension. Alright, but there's one corner case that we haven't talked about yet. Specifically, the extension pool might actually fill up and overflow as more counters overflow. To accommodate for this scenario, whenever the extension pool fills up, we repurpose it to store a pointer, which points to an external array of large counters that stores the overflowing higher order bits in plain binary. Based on the workload at hand, we auto-tune the number of counters we store in each chunk and the default short counter length within the chunks. We adapt these parameters as the workload shifts, which allows us to optimize for memory and attain the most space efficiency. Alright, so that was how we addressed the first problem of skew. Let's also discuss how to handle the second problem of stream growth. Our solution to this problem is to grow the number of counters within the sketch along with the screen. Specifically, we expand each array within the sketch to reduce the probability of hash collisions and thus the error for future insertions. So we just duplicate each array. After duplication, we have to make sure that keys map to the correct counters by employing a technique we like to call consistent hashing. The idea is that we're going to use a single hash function over the course of the filter's lifespan. This hash function is going to produce a long string of bits, of which will take some number of bits to be the address of the counter that we're going to map to. The number of bits we take will increase as we expand the arrays. So for example, initially, the key A here was mapped to the 0th counter based on the first bit of its hash. But after expansion, consistent hashing for it yields the hash 0, 1, mapping A to the second counter. In general, the new bit added by consistent hashing ensures that A will either be mapped to the same counter or its copy. This ensures that A is always mapped to a counter with consistent values. So an important question to be answered is, when do we duplicate the arrays in the sketch? As a default choice, Sublime duplicates whenever the stream length n increases by a factor of 4. So as I insert more keys, I keep track of the length of the stream and eventually duplicate the array. Of course, this process duplicates the counts of the old keys and potentially leads to large overestimations. Nevertheless, we show that the old keys whose counts are duplicated are exponentially fewer in number compared to the new keys, meaning that they contribute less and less to the overall error, allowing the error to converge. Specifically, we show in the paper that duplicating when the stream length n quadruples leads to square root n space and square root n error. Compared to a classic count-min sketch, this consumes slightly more space, but allows for significantly slower increasing errors. We also discuss what would happen when we decide to duplicate after the stream grows by a different factor. We show that the space and the error follow a pattern of n to the alpha and n to the 1 minus alpha for a value of alpha that is in between 0 and 1. So we get a full spectrum of trade-offs just by varying the duplication threshold. All right, so if we consider the space consumed by the sketch at a fixed level of error, parameterized by the stream's length, what we've discussed until now provides a upper bound on the minimum amount of space one can use for frequency estimation. In the paper, we also show a lower bound on the minimum amount of space and demonstrate that the gap between this lower bound and the space achieved by Sublime is small, thus proving the close to optimal space consumption of Sublime. Okay, let's also briefly discuss the evaluation. Here, I'm showing you the average error achieved by the sketches on the y-axis, as I vary the memory budget on the x-axis when processing a real-world stream of click data. The baseline salsa and stingy are the state-of-the-art in terms of space and insertion speed, respectively. Now, if we add Sublime to the picture, we see that Sublime attains a much lower error than these sketches at the same memory footprint. When considering growing streams as well, on a stream of English words, we see that salsa and stingy have rapidly growing errors as we increase the number of keys on the x-axis, whereas Sublime maintains a stable level of error at all times. In the paper, we discuss many other aspects of the design, including how we handle deletions, what CPU optimizations we employ to improve insertion and query speed, and the application of Sublime to other sketches, such as Count Sketch and Mies for Greece. So if you're interested in these, please check the paper out. And with that, I'll sign off. Thank you for listening.